Alright, this is the standing wave project. I'm Andrew Hawk. I will measure the room, find out what frequencies will create standing waves in this room by measuring the height of the ceiling, width of the room, and length of the room. So first off, what is a standing wave? A standing wave is when you have a set of parallel walls. So what will end up happening is certain frequencies where the wavelength is just right will reflect perfectly off the wall and then intersect with itself. This can create a problem because what will end up happening, you have nodes and antinodes where the volume, because of this, the volume can be louder or softer. So specifically, a node is when the crest of the wave will intersect with its own trough. So what that does will kind of create a noise or a sound cancellation. You'll have a much quieter volume. And then the opposite would be the antinode, and that is where a crest will intersect with another crest of itself, or a trough will intersect with another trough of itself. And so what that will do is make the volume much louder, the perceived volume. So, this could definitely be a problem in mixing or recording, where you really need to get your volume set and make sure everything, is just as loud as you want it to be. So, how I'll go about doing this, I'll measure, and then I will use a formula. But first we have to know, the speed of sound. This is backwards if this helps at all. But the speed of sound is 1,130 feet per second. Again, I know that's backwards, so that may or may not be helpful. But where that fact comes into play is with this equation. This is lambda equals velocity over frequency. So lambda is wavelength in this case, which will be the length of the room or height or width. Velocity will be, again, the speed of sound. So we are solving for frequency. So with a little bit of algebra, you can just remap that to be frequency equals velocity divided by wavelength. So with that, I will get to measuring with the glorious tape measure my roommate was so graciously willing to lend me. Just have to put this up here. There we go. And that's looking nice and pretty. That's alright, because luckily I had my hand on the tape measure. Alrighty. And looks like the height of this room and the frequency that will lead to our first standing wave is 9 feet on the dot. So we will just write that down, or I will. 9 feet. Alright. Next, I will find the width. And to do that, just measure this. And looks like that is Thank you, Patrick. That is someone who is outside of the practice room. Anyway, sorry I got distracted. But that's what happens when you use a space that other people use as well, I guess. But that's alright. So, let's do a quick remeasuring here. And boom. Alright. So that is 5 feet and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 inches. 5 feet, 10 inches. However, we want this all in feet, So we have the 5 feet. To find out how many inches or how many feet 1 inch is, we're converting it to essentially tenths of a feet. So what we will do is calculate here. All right. So 0.08333 repeating that's how many feet are in 1 inch. So we'll head over to my calculator here on my computer. 0.083, that's 3 significant figures. 0.083, yes, times the 10 inches that we have. Let us add on 0.83 feet to our pre-existing 5 feet. All right. So, back to measuring. Get the length now. Go on this wall here. Get a nice solid measurement. Alrighty. So this looks like 9 feet. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 again. Right, well, that's convenient. So we already know, well then, we know that's 0.83 of a feet. 10 inches is 0.83. So we will take 9 feet, 9.83 feet. Wonderful. So, the height is 9 feet, the width is 5.83 feet, and the length of the room is 9.83 feet. Again, I apologize that it's backwards. Sadly, I'm not adept at writing backwards so that it appears forwards. So, now we add that into the calculations here. Plug the feet in for lambda, and the velocity will be the speed of sound, again 1,130 feet per second. So for the first one, we will take 1,130 feet per second, the velocity divided by lambda, the wavelength, of 9.0 feet. We have 3 significant figures. So that comes out to be 126 hertz. It's in hertz because that is waves. All right. Or pulses. Next, we will take, so, first standing wave, the first frequency we know that will start to create issues depending on where you're located in the room, because, if you're located near an antinode, it'll appear, that frequency will appear louder. If you're located, like if you're standing in an area where there's a node, then it'll appear much softer. So, next we'll take 1,130 divided by 5.83 feet, and we get 194 hertz. Wonderful. 194 hertz. All right. And last but not least, we have our length for the third and final standing wave, which again is 1,130 divided by 9.83. And for the final troublesome frequency of 154 15 hertz. So, for this room, frequencies that will create standing waves: 126 hertz, 194 hertz, and 115 hertz. Again, depending where you are located, those specific frequencies will sound either louder or softer. So, there you have it. That's how we can find out some standing waves in your room. And remember, this is only the case in parallel walls. A way to remedy standing waves is to set, either angled walls. Sometimes, even the ceiling and floor will be angled because, those are walls too. Or to even just have, some like mesh stuff that'll, have an angular surface along the wall. Same with the ceiling. So that's it, and there you go.